Hello. In this video I'm going to do another example of a numerical integration. I'll be using the trapezoidal method, but this is a situation where we start with a function rather than a set of data points. Suppose that f of x is defined as the function 1 over the square root of 1 plus sine x. So f of x has this particular definition. If we plot a graph of this function, we get a curve that looks like this. It's concave upwards. It then has a pole here where sine of x is -1, and then it descends beyond that. And what we want to do in this particular example is to get an approximate value for the integral from 1 to 4 of 1 over the square root of 1 plus sine x dx. The dx here means we're going to work along the x-axis. The 1 over square root of 1 plus sine x is the integrand, and that is this curve, and we're going between the limits 1 and 4. And we're going to find an approximate value for this particular function by using the trapezoidal method of approximation. Okay, so the way we start is we collect a bunch of data points for this function. Here we have x. The x values 1, 1.2, 1.4, 1.6. It looks like I've always used the same interval of 0.2. That's nice. And we have the function values, and we have calculated these values for this particular function. And over here in this column I've put the trapezoidal weights that we will use. Now at the end of the previous video I showed how you get these weights, and I'll do that again here. But the method is simply that you multiply the function value times its weight and then add up all the answers you get. Most of the time you're going to multiply by 1, so it's the same number. But there, first and last, you multiply by 1/2. So why do I have those particular weights? Well, remember the trapezoidal method works on a straight line approximation, and the area under this curve for this particular data set, which is the one we used before, is the area of that trapezoid, which is its length of the base times the average of the two sides, 7 and 10. And here the area of the second trapezoid is the area length of the base, 5, times the average of the two sides, which is 10 and 4. And so the trapezoidal method would say we approximate the area under the straight line curve rather than the function curve itself. So the calculation goes like this. We have a common interval length 5 that we factor out. Inside the bracket we have a 7 plus 10 over 2, the average on the first interval, and 10 plus 4 over 2, which is the average on the second interval. If we expand these, take away the common denominators, we'll get 7 over 2, 10 over 2, and 10 over 2 plus 4 over 2. We can add the two 10 over 2's together to just get 10. And this same pattern will repeat if we have more intervals. We'll just get the data values for everything but the first and last, and the first data value is divided by 2 and the last data value is divided by 2. And that's where we get these trapezoidal weights from. We weight the first by 1/2, the last by 1/2, and everything else by 1. So it's easy to do that calculation. You can use an Excel spreadsheet. And what you get is that with an interval length of 0.2, you get an area under the curve of 2.8436. If we went to half that length, we would get 2.8366. So that's a smaller number. And you can see why the smaller numbers will be coming in, because the between 1 and 4, the curve is concave up, so the straight line approximation will always be above the curve, and so the straight line approximations, all of them will give over estimates of the area, But as we make a finer approximation, we will get lower values here. It looks like 2.8 is already a good approximation for the area. Okay, let's just wrap up with a summary. The calculations of the trapezoidal method are easy when the intervals all have the same length. They get a little bit more difficult when you have different intervals of measurement. Shorter intervals usually give better approximations, and the trapezoidal method calculates the area under the straight line approximation to the curve. And for shorter lengths of interval, you will get a better approximation. I will say that the trapezoidal method is calculating with the straight line approximation of the curve. When we do the theoretical background to integral calculus, it's more customary to use a different numerical integration model, which is the left-hand endpoint or the right-hand endpoint for the intervals. But when you're trying to visualize what's happening in a numerical integration, I think that the straight line approximation of the curve is a much better one to start with.